What is a complex number? A complex number is a number that contains a real component and an imaginary component. So A is standing in for the real component and B is standing in for the imaginary component. An example of a complex number would be 5 plus 6i. So the real component is 5, imaginary component is 6. In another video, we looked at how we get I and what I represents, and then we looked at graphing these complex numbers. In this video, we're going to look at performing operations with complex numbers. The three operations, that we're going to look at are adding, subtracting, and multiplying. You can also divide with complex numbers, but it gets a little complex. And so we're just going to focus on these first three in these videos. Adding and subtracting complex numbers means adding the real numbers together and adding the imaginary components together. So if we have the complex number 3 plus 4i, and we were going to add it to the other complex number 5 minus 6i, all we would need to do is combine or add the real components and then combine or add the imaginary components. So for the real components, we have 3 plus 5, and that would be 8. And we have 4 and negative 6, so for the imaginary component, we have minus 2i. That means our final answer is 8 minus 2i. And that's it. That's how you add complex numbers. You can also subtract complex numbers in a pretty similar way. Say we had 6 plus 9i, and we wanted to subtract the complex number 3 minus 2i. What's a little bit different here is we're subtracting the whole complex number. So we can think about distribution. This is really the complex number 6 plus 9i minus 3 plus 2i, because we're distributing that negative sign. Now it's just a matter of combining like terms or putting the real numbers together, 6 and minus 3, which is 3, and the imaginary numbers together, 9 and 2, so that would be 11. So our final solution is 3 plus 11i. Adding and subtracting involves putting the real part together, putting the imaginary part together. Let's look at another couple adding and subtracting examples before we move on. How about the complex number 2 plus I, and let's add that to the complex number 2 minus I. Since we're just adding, we can just take the real components, put those together, the imaginary components, I plus minus I, that's nothing. So the solution to this addition problem is just the real number 4. The i's canceled each other out. This is kind of a special example because 2 plus I and 2 minus I are called conjugates. Conjugates of complex numbers is just if you have a plus bi, its complex conjugate would be a minus bi. Whenever you have this, some special things are going to happen with adding and subtracting. In this case, we saw that the i's canceled out. That's what happens when you add them together. When you subtract them, well, let's try an example with subtracting. 2 plus I minus 2 minus I. Here we're distributing the negative. So we get 2 plus I minus 2 plus I. Okay? So combine like terms, 2 minus 2, I plus I. Our final solution is 2i. So we can see when we subtract conjugates, the real part goes away this time, and we're left with just the imaginary components. Now let's look at multiplying complex numbers. It's actually kind of similar to how we multiplied polynomials or binomials. So we can use something similar to double distribution. Let's try the number 3 plus 2i, and we're going to multiply it with the complex number 4 minus 5i. So when we do our distribution, we're going to start with the 3. We're going to multiply everything by 3. We're going to end up with 12 minus 15i. Then we'll continue our distribution and we'll multiply everything by 2i. So we're going to end up with 8i and negative 10i squared, because I times I would get us I squared. Well, when we continue this a little bit, we're going to end up with 12, and then these i's can go together, and negative 7i. And now we're left with minus 10i squared. Well, remember, what is I squared? I squared is negative 1. So this is the same as saying minus 10 times negative 1. So we have 12 minus 7i plus 10. Well, that means we actually have a couple more like terms. 12 is a real number and 10 is a real number. So our final solution is 22 minus 7i. So we used the similar technique to double distribution, but we needed to remember our I squared is negative 1 so that we could see what were the really real components and what were the imaginary components. Let's try another couple of these. 3 minus 7i all squared. If you recall from our distribution videos, that when you have a whole component squared, really it just means times itself again. So this is 3 minus 7i times 3 minus 7i. Now we can use distribution. So we end up with 9 minus 21i, that's 21, minus 21i plus 49i squared. Remember, what is I squared? I squared is negative 1. So we could really say that we have 9 minus 42i minus 49, because negative 1 times 49 would be negative 49. So we can see that we actually have two real components here. We have 9 minus 49. So our final real component is negative 40. Our imaginary component is negative 42i. So our final solution to this multiplication problem is negative 40 minus 42i. 5 minus 2i and 5 plus 2i. Do you remember what these are called? These are complex conjugates. We saw what happened when we added conjugates, and we saw what happened when we subtracted conjugates. Let's see what happens when we multiply them. Start out exactly the same. Really, this is just a regular old multiplying problem. We're going to end up with 25 plus 10i minus 10i minus 4i squared. Remember what our I squared is. That's really negative 1. So we have 25 and 10i's minus 10i's, they go away. So we have 25 plus 4, because I squared is negative 1, and we have 29 as our final solution. So when we multiply complex conjugates, the imaginary parts go away, and we're left with just a real number. Here's a doozy for our very last problem. It requires us to do all sorts of different multiplication and even some adding and subtracting too. That's okay, that way we only have one example left. Yay! So let's go ahead and start with that 3 minus I. 3 minus I squared means, remember, 3 minus I times 3 minus I. So that's going to get us 9 minus 3i minus 3i plus I squared. Remember what I squared is. So we get 9 minus 6i minus 1, because I squared is negative 1. So we get 8 minus 6i. Now we need to think about the rest of the problem. Let's distribute that negative 6, just like you would with polynomials. I'm going to rewrite this all the way down here. We're going to end up with negative 6 plus 12i. Last but not least, we have I cubed. If you think back to our I video, I cubed is I times I times I. I times I is negative 1 times I is negative I. So here's where we're at down at the very bottom. We have 8 minus 6i minus 6 plus 12i minus I. Adding, combine all the real, combine all the imaginary. So 8 minus 6, those are the only real ones, so I end up with 2. And then the imaginary components are negative 6, positive 12, and negative 1. So negative 6 plus 12 is 6, minus 1, and we end up with 5i. So just a little recap on this one. We saw all the different components of operations with complex numbers. When we add and subtract complex numbers, we just need to add and subtract the real numbers with the real numbers and the imaginary components with the imaginary components. When we multiply, it's similar to double distribution. We always need to remember that I squared is negative 1 so that we can find all of the real components to our final solution. Now I'm going to look at just another couple of things with adding and subtracting that will help us solve some of our quadratic equations that have imaginary solutions. If you have a complex number that's equal to another complex number, here's what you know. You know that the real part of one number is equal to the real part of another number, and the imaginary part of one number is equal to the imaginary part of the other number. So in this one, it's kind of silly, but x would equal 9 and y would equal 2. Well, let's look at one that's not quite as silly. Let's look at 3x plus 5i equals 9 plus 2yi. So the real component of the first one is 3x. That's what doesn't have the I. And the real component of the second one is 9. So I know that 3x equals 9. Solve. And we found x. X equals 3. And the imaginary component of the first number needs to equal the imaginary component of the second number. So 5 equals 2y. Divide both sides by 2. We get y equals 5 halves, or 2.5. This was just a little extension where we could see that if we have two complex numbers that are equivalent, their real part is equivalent to the real part, and the imaginary part is equivalent to the imaginary part. That's a big theme in complex numbers, is looking at the real and the imaginary parts separate to combine them, whether you're adding, subtracting, solving these types of equations.